Okay, thank you, Dr. Erickson, for accepting the invitation to deliver your topic in this seminar from the Citedi, the Polytechnic National Institute in Mexico. I will introduce Dr. Erickson. Robert Erickson is a professor in the Department of Electrical, Computer, and Energy Engineering at the University of Colorado, Boulder. Dr. Erickson is a director of the Colorado Power Electronics Center and an author of the textbook Fundamentals of Power Electronics, currently in its second edition. Dr. Erickson has been recognized as a fellow of the IEEE and a fellow of the joint DOE National Renewable Energy Laboratory and University of Colorado Renewable and Sustainable Energy Institute. Dr. Erickson earned the BS, MS, and PhD degrees at the California Institute of Technology, Pasadena, California. For 36 years, Dr. Erickson has taught courses on power converters and other electrical engineering courses at the University of Colorado Boulder. Dr. Erickson's research is in the area of power converter technologies, topologies, modeling, and control, and he's a recipient of awards including the IEEE William E. Newell Power Electronics Award, UC Boulder Inventor of the Year, and IEEE Transactions on Power Electronics Prize Paper. And he will be talking to us. His topic is complexity and modularity in high power SiC converter architectures. So thank you, Dr. Erickson, and you have all our ears.
Thank you, Ms. Rain, and thank you for inviting me to give this talk and the opportunity to present. Please feel free to ask questions and interrupt at any time, that's fine. So yes, I want to just talk about my research directions in the power electronics area to try to improve and advance the technology of power converters. And what's really happening is that the field is being revolutionized by the introduction of new kinds of power transistors. And basically with wide bandgap devices now, we can extend high frequency switching converter technology to much higher power levels and the applications that go along with those. So I want to talk or think a little and talk about how to do that in the best way. So I have a brief, I guess, introduction to what power electronics is for those of you who aren't familiar with the field. And then I want to talk some about research projects I've been working on and about this topic. So the main point here is that at these higher power levels, it becomes, well, they necessarily involve many power semiconductor devices to meet the requirements of the power level. And the best way to use those devices and to connect them in circuits to perform the best is actually much greater complexity. Highly modularized and much more complex systems can fundamentally do the power conversion job better. And we'll talk about what better means also, but we can really make fundamental improvements in the technology of power electronics through these more complex power converter circuits and control. So again, research directions, the trends are higher voltage and power in power electronics by these new devices, and the solutions that work better have higher complexity. And so we need to think about how to build larger, more complex power converter circuits to do this job. Some of the emerging applications, certainly electrified transportation is very important today with electric vehicles, electric trucks, electric or electrified construction equipment, like very large tractors and caterpillars, and electrified airplanes. And now we have companies building electric airplanes as well. Fast charging of electric vehicles is important. And to charge your electric vehicle in 10 or 15 minutes, we now have some cars with battery or water-cooled batteries that can do this. But they require very high power. So 500 kilowatts, half a megawatt, or even a megawatt, that is much greater power than we're used to having in, just around town. And then we have microgrids and, more robust power systems that can operate when they're disconnected from the rest of the grid. So here I've shown an electric vehicle here, and it's actually being charged wirelessly by a wireless charger in the bottom of the, oh, let's see, I'm not.
Yeah, you're.
Am I sharing my screen?
No.
No, sorry. Okay, here we go.
Okay. Okay, now we can see it.
Yes. So here's an electric vehicle, and it's being charged wirelessly by an inductive wireless charger on the floor. And there's a lot of interest in high power wireless charging for electric vehicles. Here's another example of a utility scale power converter that converts DC to AC in the grid. And each of these nodes is actually a small power converter, and it's highly modularized. Some of the metrics that are important: power density is a traditional metric of power conversion. So this is how much power can you get for a given volume or weight. This is maybe not so important in this utility application, but it's extremely important in electrified transportation. So like in electric vehicles, the weight really impacts the range of the car, and the size, there isn't much room on the car to efficiency and Q. We'll talk in a minute about what I mean by Q, but efficiency always is important. And the reason, of course, we don't want to waste power. We want to conserve power, but even more important than that is that if your power converter processes significant power and it's not very efficient, then it gets hot and you have to cool it. And so it needs large heat sinks. And really, the power density or size of the power converter is really driven by the size of the heat sinks, which then are driven by the efficiency. So to make our power converters small and lightweight, we need high efficiency so that our heat sinks are small. We'll talk about mean time to failure. Reliability is a big problem, and I'll come back to that. And of course, everyone is interested in low cost. So just a little background for those of you not familiar with power electronics. Here's a one-slide introduction. These power converters that we build efficiently change electrical power from one voltage to another and from one current to another. And we do it with what are called switching converters. Here I've represented the switching converter circuit here as one that I've drawn with an ideal switch. In practice, the ideal switch is actually realized with power transistors that switch on and off to perform the switching function. And the point of using switches is that they're nearly 100% efficient. When the switch is closed, there's very little voltage across it. When the switch is open, there's no current through it. And in either case, the power lost in the switch, which is voltage times current, is low or near zero. What we do with a switching converter is we turn the switches on and off very quickly. In this particular circuit called the buck converter, we vary the switch position between position 1 first so that the voltage coming out of the switch is equal to the DC input voltage, VG, like that. And next we change the switch to position 2. So connect it here. Then the voltage coming out of the switch is 0, like this. And so we produce a switched voltage waveform that switches high and low, like this, repetitively at some frequency we call the switching frequency, or with a period that's 1 over the switching frequency, that is this distance, T sub S, it's the switching period. And it has a duty cycle. So the switch is in position 1 for some fraction of the time, D, and it's in position 2 for the rest of the time. What we accomplish with this is to change the DC component of the voltage. So our input DC voltage is VG. This switch waveform coming out of the switch network has a DC component from Fourier series, that is the average value. So you integrate over one period and divide by the period to find the DC component. Excuse me. The integral is this area, which is the height VG times the time dTs. If you divide by TS to get the average, we find that the output voltage is the duty cycle D times VG. The duty cycle is the fraction of time the switch is in position 1, so it's some number between 0 and 1. And what the switch network does is change the DC component from VG to this new average value that's smaller. Excuse me. Okay, and we've just used switches that ideally don't consume power, so it can be very efficient. What is left then is to add a low-pass filter, which is this LC network, that is designed to let the DC component pass, but filter out the switching harmonics, so that the output voltage is essentially equal to the DC component. And what comes out of the circuit then, at this point, is a reduced DC voltage equal to the duty cycle times the DC input voltage. So this is called the buck converter. Buck means it reduces the voltage, and we're able to change a higher voltage into a lower voltage. There are no elements that consume power, at least to the extent they're ideal, and so this circuit could be 100% efficient if all the elements are ideal. So by reducing the voltage and being 100% efficient, it increases the current, and it has current gain. It's a near lossless way to convert voltage and really to control the voltage simply by changing the duty cycle or the timing of the switching. We can control the output voltage and regulate it. Another important and basic converter circuit is called the boost converter. I won't belabor it, but basically it's a buck converter connected backwards. So the position of the switch and the inductor are reversed here and here. And what it does is it increases the voltage instead of decreasing it. So the boost converter has voltage gain. Its output voltage goes like 1 over the duty cycle, or actually 1 over 1 minus the duty cycle. And it has voltage gain, and it reduces the current, and ideally is lossless. There are many ways to build networks of inductors, capacitors, and switches to convert voltages from one voltage to another. And at these higher power levels where we naturally need high power switches that are actually many semiconductor die, we can do better and build more efficient and more compact power converters with circuits that are considerably more complicated than this. And so this is a topic of current research of what is the best way to do it. So I've been working on electric vehicle power electronics, and I have a current research project on that. This work really took the Toyota Prius as a starting point. And here's a diagram of the power electronics or drivetrain of the 2010 Toyota Prius hybrid electric vehicle. This vehicle has a battery. I guess back in 2010, it was a nickel metal hydride battery that was nominally a little over 200 volts. It would vary from 150 to 300 volts. There was a boost converter, which is this, that has power transistors. These are silicon insulated gate bipolar transistors to produce an increased voltage on a DC bus that could be as high as 650 volts. It's actually controlled and varied according to the speed at which the vehicle runs. And then there are inverters, and each of these inverters for each phase has a switch network along with the inductor in the winding of the motor that is basically a buck converter. So one phase of an inverter is basically a buck converter and produces a voltage applied to the motor that is less than the DC bus voltage. The motor wants its voltage to be, or the motor voltage naturally is proportional to the motor speed, and at different speeds we need different voltages. So one way to control the Prius system is for the boost converter to raise and lower the bus voltage according to the speed. And then we have these inverter circuits to control the currents going to the motor and control the torque. In the 2010 Prius, the boost converter is rated 30 kilowatts. And in other larger hybrid electric vehicles, these converters are 100 or several hundred kilowatts. Here's a plot of a prototype in our lab. And what's plotted here, this is over what's called a drive cycle. And we have these standard drive cycles in the electric or in the transportation business to model how cars are used. The US 06 drive cycle is one that is viewed as aggressive driving. So it has higher power and perhaps is a more fun drive cycle. So it's the speed is plotted here, and the voltage of the bus is proportional to speed. The blue curve here is the vehicle speed versus time, and this is from 0 to 600 seconds. So 10-minute drive cycle, and we accelerate, slow down, and so on. Other waveforms here are the motor voltage and current and the DC bus voltage. So this, I guess I'd say this is a typical usage of the power electronics, and these standard drive cycles are how we model how the power electronics would be used in a real situation. Okay, I think the history of power electronics, of course, we want everything to be low cost, we want low loss, so we want high efficiency, and we want small size, so small volume and weight. And of course, if we could build converters where the cost is 0, the loss is 0, and the size is 0, then we would have power electronics used everywhere. And in fact, we're trying to do that, of course, and use power electronics everywhere. But the history is that people would achieve these goals by means that were not really not theoretically sound. So they would make the heat sink too small to reduce the size, and the converter would overheat, run too hot, and have a short lifetime. And so In the United States, there was a U.S. Navy committee that was formed to recognize the problems of unreliable power electronics. And they actually proposed some ways of measuring reliability that have now become used in industry around the world. And there are different ways of calculating, mean time to failure or lifetime based on standard formulas. And the object was try to model reliability and then use it to judge how good a technology is. And so not only do we make things low cost, low loss, and small size, but we need to do it with high reliability. Okay. Traditionally, we talked about efficiency, which is ratio of output power to input power, and we want high efficiency. With a power converter, though, really efficiency isn't the right measure. For example, if you increase your efficiency from, say, 92% to 96%, it's 4%. So you might get 4% more power out of your power converter. Most people will say, well, that's nice, but it's only 4%. It sounds incremental. But in fact, what you're doing is cutting the loss in half, going from 94 to 90, or from 92 to 96. You're cutting your loss in half, and the loss is going from 8% of the output to 4% of the output, and you can make your heatsink half as large and still have the same temperature rise. So really a better measure where we're trying to have a giant conductor coming in with a lot of power and have a tiny power converter and a giant conductor coming out, really the best measure we redefined as Q, which is the power converter quality factor, and it's the ratio of output power to loss. So really, output power is given by the application, and loss is something we want to minimize. And so if you can double the Q, going from, say, 98% to 99%, you're cutting your size in half. And so we've now kind of switched to talking about the Q, and that's really a measure of a power electronics technology. Okay, I think this is my last little background slide. Silicon carbide devices. I guess we have wide bandgap devices now. The traditional power semiconductors were made out of silicon, and today we have wide bandgap devices. Silicon carbide and gallium nitride are the two commercially available power devices now. In the case of silicon carbide, you can get silicon carbide MOSFETs at ratings up to 10,000 volts, which is pretty amazing. And these devices, not at 10,000 volts, but at over 1,000 volts, they can switch at switching frequencies more than 100 kilohertz, as opposed to 1 kilohertz for a high voltage silicon IGBT, or insulated gate bipolar transistor, as is what's used in the Prius. The Prius uses 1200 volt silicon IGBTs that switch at 10 kilohertz for reference, and its inductors and capacitors are sized accordingly. When we go to higher frequencies, the size of the inductors and capacitors decreases, basically is the inverse of frequency. And so going to higher frequencies can lead to great reductions in the sizes of the reactive elements. So we have the opportunity then to use these wide bandgap devices at high voltages and the high powers that go along with them, and run them at much higher frequencies. The problem is the wide bandgap devices cost, they're very expensive. They're 5 or 10 times more expensive than the old silicon devices. And so if you just replace the silicon device with a silicon carbide device, it can switch faster, but usually the increase in Q is not that great. And the cost is very great. So what people have understood in the industry is that we need to redesign the whole converter and find new ways to use these devices in these applications that are possible at these higher voltages. So for example, in electric vehicles, in utility scale solar plants, in electrified trucks and airplanes and similar kinds of things. So there are some things we can do that fundamentally improve the performance of a converter. And generally they require higher complexity and and more complexity both in the converter circuit and in its control. So multi-phase conversion is one of these. Here is a buck converter. So this is the DC input, and we're making a lower voltage DC output. And what we have are two buck converters that are connected in parallel. So each is a switch. It has a power MOSFET to put the switch in position 1 and another one to put it in position 2. And it has an inductor to filter the switched voltage that appears here to produce a lower voltage and higher current output. These inductors are filtering the switching harmonics, and they have a switching current ripple in them that is further filtered by the capacitor. And what we do with multi-phase conversion is we'll build more than one phase, and we'll operate the two different phases 180 degrees out of phase, so that this inductor current maybe goes up and down looking like that. This inductor current in the other device goes down when the other inductor is going up, and it's out of phase. So when you add their currents, they tend to cancel, and we can greatly reduce the size of that capacitor. So multi-phase conversion is another way where we're saying, okay, we're going to use a lot of devices anyway in a high power application. Let's use them more intelligently and do multi-phase conversion to further reduce the size of the capacitors. So then our capacitors are less expensive, and that can at least partly make up for the increase in cost of the transistors. We also have what's called multi-level conversion, and in some ways this is the dual of multi-phase conversion, where instead of having the current waveforms out of, having two sets of currents that are out of phase, we have two sets of voltages that are out of phase. So here's one converter and here's another, and we can actually produce a switched voltage that has, instead of just going up and down like this and having two levels, we can produce a voltage waveform that has a third level in between. So we could make voltages that maybe do that. With multi-level conversion, we're able to reduce the voltage, the AC component of voltage that comes out of the switch network, and have smaller inductors. So this is the dual of multi-phase conversion. It reduces the voltage ripple that is filtered by the inductor and allows the inductor to be smaller. It also reduces the voltage that is applied to the transistors. You can actually, with this circuit, get half the voltage stress that you would have with this. So we can use lower voltage transistors, which have better characteristics. So this is more complex, and it needs more complex control, but we can fundamentally reduce the sizes of the inductors and capacitors simply with a more complex power converter and switch network. One of the complaints about higher complexity is that if you just count the number of transistors, there's more. And when you have more devices added into your formula for reliability, it says that more devices will fail more often and the lifetime is lower. So one of the battles here, I guess, is to convince people in industry to use these more complex circuits when there are more devices. But that statement really is not fair and it's not correct. At higher power levels, we take more devices, more semiconductor die, and package them in parallel into a larger semiconductor high power package. And then if you count that as one transistor, it's not fair. And here I'm really saying that let's take those same die and just connect them in a better way. And and by connecting them in a better way, we can actually reduce the size of our inductors and capacitors, and we can reduce the loss and build a more efficient circuit that actually runs with lower temperature rise. So research here is really saying that with these more complex converter architectures, we can fundamentally improve the system performance as measured by power density, really the size of the inductors and capacitors and heat sinks, and through this Q, or ratio of output power to loss. If you keep all other things the same, we have lower temperature rise with lower loss. Lower temperature rise improves the mean time to failure. And we can actually, with more devices, get better reliability, not worse. Here's a plot of that boost converter, 30 kilowatt boost converter in the Prius. And this curve is the efficiency curve for the 10 kilohertz silicon boost converter that was in the 2010 Prius. And what we're doing, or the approach that I'm proposing, is able to take the devices, connect them in a more complex but better way, and get this efficiency curve. Okay, and it has really two good things. Of course, the efficiency is higher at full power, but also at low power, we maintain high efficiency. In fact, this thing maintains this high efficiency of over 98% all the way down to 1 kilowatt. So from 30 kilowatts to 1 kilowatt, it's basically 98% efficient. Whereas in the actual converter, this simple boost converter used in the Prius, the efficiency drops off at low power. Okay, so this has a big impact also on the temperature rise with real drive cycles. Think about how you use your car. You can only, push the accelerator to the floor and leave it there for a few seconds. Sooner or later, the car is going too fast and you stop accelerating. Under normal driving conditions, you use high power only a small fraction of the time. Most of the time, we're maintaining constant speed and we're down here. We're at relatively low power. Maybe we need high voltage, but we don't need high power. So the efficiency curve has a big impact on the total loss and then the average temperature rise over the lifetime of the car. So this project I'm doing now, it's actually in collaboration with Toyota, and it's a U.S. Department of Energy sponsored project, is really to demonstrate this at the 100 kilowatt level with lithium ion batteries that work over a 200 to 400 volt range and can boost the voltage up to 1200 volts. So higher power levels and higher voltages in your car. And we also want to incorporate charging and we want to be able to control this thing. Um, let me talk for just a second about power loss. So far, everything I've described in the circuit has been ideal. If we categorize the different kinds of losses in a switching converter, we can put them into two large categories, one called direct power and one called indirect power. Direct power is the power that flows from input to output directly as DC, and it's not converted from DC to AC at the switching frequency and back to DC. If you just turn your MOSFET on and leave it on, so the duty cycle's 1, it simply connects the output through the inductor and the MOSFET to the input. The output voltage equals the input, and we have DC power flowing from the input to the output. And that's called the direct power path. The only losses we incur are from the resistance of the inductor winding and from the forward voltage drop of the MOSFET. Direct power tends to not have very large loss. Then we have indirect power. And indirect power is the process in which the transistor switches and converts some of the DC input power to AC at the switching frequency. That power, AC power, is temporarily stored in the inductor, and then when the diode conducts, it's rectified by the diode actually back to DC and flows to the output. Indirect power is the process by which converters have gain. So in the buck converter has current gain. It steps down the voltage and steps up the current. So the output current is bigger than the input current. Where does that increased current come from? Well, it comes from here. And what's happening is some of the input voltage appears across the transistor. The transistor switches, stores it in the inductor and releases it from the diode. And we have some diode current and power and some transistor current and power that add to make more output voltage or output current. In the boost converter, we have voltage gain, and in a similar way, we're getting that through indirect power. So whenever the output voltage is different than the input, there has to be some indirect power. Here's a little proof. I don't know if I want to spend the time doing proofs, but you can show that there is actually effectively some average voltage across the transistor and average current through the transistor, which looks like there's average power going into the transistor. But actually, there's AC power coming out of the transistor that is getting rectified and coming through the diode. So some of the power goes into the transistor, comes out of the diode, and that's the indirect power. The problem with indirect power is that at the switching frequency, we have all these additional loss mechanisms. There's switching loss in the transistor that occurs during the switching transitions of turning the transistor on or off, where it shorts out its output capacitance and the energy stored in that is lost in the transistor. There's diode reverse recovery that induces switching loss in the transistor. And the inductor has AC losses, core loss and the skin effect, AC proximity losses in the conductors. So all of these things, these additional loss mechanisms happen from indirect power. So this indirect power mechanism is needed for power conversion, but it is the major loss mechanism that we have in switching converters. And so the goal then is, how do we convert the indirect power in the most efficient way possible? And the basic circuits that we know aren't the most, they're demonstrably not the very best we can do. So it's, I guess people in the power electronics field have learned that there are certain circuits we can build that can convert indirect power very efficiently. And the best one I know is called a DC transformer. It's a, it's a circuit that switches. And if you just look at its external characteristics, there's a DC input and a DC output. The ratio of them is the turns ratio of this physical transformer, but there's switching on both sides of the transformer. Basically, DC input power is converted to AC. It's put through the transformer and converted back to DC at the output. And it turns out that we know how to design this circuit to be super efficient at 1 voltage ratio, where the voltage ratio is equal to the turns ratio of this transformer. It's possible to operate this circuit at other voltage ratios, but then the efficiency gets bad quickly. But if all you want to do is have a fixed voltage ratio of DC voltages, then this circuit can do it. It also turns out that when it works at that ratio, the capacitors can be very small. The optimal current waveform in the transformer winding is this trapezoid that looks like that. You put that current through the transformer, and then this output side rectifies it so that the current coming out here looks like this. So the bottom half, the negative half of the current waveform, is rectified to become the positive half, and the current coming out of here is almost DC. Excuse me. There's a little bit of a notch there that has to be filtered by the capacitor, but the amount of capacitor we need is very small. So this is, in a lot of ways, a very good circuit if all you want to do is operate at a fixed voltage. Here's a plot of the DC loss of a boost converter from the direct power as a function of duty cycle, and the AC loss from the indirect power. Higher duty cycles make higher output voltages, but as we go to higher duty cycles to boost the voltage more, we incur a lot more AC loss and the efficiency goes down. So the question then is, can we find a way to use DC transformers to convert at least part of this AC indirect power and reduce the AC loss? So the approach that we've taken, we call composite converters, or a composite converter architecture. The composite architecture is a collection of possibly dissimilar partial power converter modules that are arranged in a way to reduce the loss of the indirect power. And so in the Prius, they have big 1200 volt power transistors. Each of these power transistors is actually multiple semiconductor die that are connected inside a larger package and put in parallel. And so again, what we're saying is, all right, let's take that die and use it in a partial power converter here. And if control these modules and connect them in a way that is optimized for the application. And here for the Prius, then we want to choose this architecture of composite converters with partial power converter modules to minimize the loss over typical drive cycles. So the plot of efficiency that I showed on a few slides ago was this architecture. And that architecture was chosen and highly optimized to work over standard drive cycles that we take as models of how the car is used. Okay, so this composite architecture has a boost module in it, but the boost module doesn't have to boost the voltage very much. So if you go back and look, the object is to get the boost converter so that it only has to work down here and don't work it at high duty cycles. If we don't try to boost the voltage too much, the boost converter has very high efficiency, and the efficiency drops off up here at high duty cycles. So you could begin to see that the boost converter here is this architecture is chosen to minimize the range of duty cycles over which the boost has to operate. We have a DC transformer here that is able to take the input voltage and stack it on top of the boost to produce additional output voltage. And then there's a buck converter to be able to control the voltage that the DC transformer produces. And we looked at a lot of different architectures, but this was one that we decided was optimum. So we can actually reduce the capacitor currents, reduce the inductor size, and reduce the loss, all by minimizing the amount of indirect power. I guess this is what I just said. I've drawn the transistors here in the buck and the boost. So basically, the output voltage is this combination of voltages produced by the boost converter and produced by this upper series connected leg. We can choose the turns ratio of our DC transformer. It's actually a design variable, and we can try to optimize the split between this power path and that power path to minimize the loss over a typical drive cycle. Here's an example of taking a 200 volt input in the Prius and making 600 volts out. And one way to do that is to choose our DC transformer turns ratio of 2. So that if you apply 200 volts to the DC transformer input, we'll get 400 volts out. To get 600 total, the boost doesn't actually have to do anything. It can simply connect the input to the output and make 200 volts. So that's called pass-through mode, where we don't actually switch the transistors in the converter and we simply connect the input to the output. Pass-through mode has no indirect power, no AC loss, and it's very efficient. So here's an example where the buck is in pass-through mode. It's connecting its input to its output so that we have 200 volts here. The DC transformer is running. It's making 400 volts with very high efficiency. And the boost is in pass-through mode, so its loss is very low. And we get super high efficiency with 600 volts out. Now, if you want to make lower voltage, what you can do is turn on the buck converter to reduce the voltage, reduce the 400 volts to a lower voltage. So then the buck converter starts switching. And if you don't try to reduce the voltage too much, so you're close or neighboring to the pass-through mode, you still get pretty high efficiency. Likewise, if you wanted to increase the output, instead of 600, say 700 volts, then leave the buck in pass-through, but start switching the boost to boost its voltage to make, say, 300 volts out of the boost. So then the boost is increasing 200 to 300. that still can be done at a low duty cycle with pretty low loss. So we can get very high efficiency at 600 volts, and at neighboring voltages, we switch the boost or the buck, one or the other, and can control the output, but with some still have very high efficiency. The system efficiency here turns out to be 98.5% if our DC transformer is 98.5%. Here's some other examples of composite architectures, and there's simply a collection of different partial power modules arranged in different ways to do different jobs. So this is a boost type composite architecture with 3 modules. Here, if you connect it backwards, you get a buck type composite architecture. Here's some ways to get buck boost type architectures with 4 modules. And you can start inventing all kinds of architectures with different combinations of modules. We won't go there, but the boost architecture is one that finds a lot of application in the powertrains of certain manufacturers of automobiles like Toyota. Caterpillar uses the boost architecture in some of their large earth movers that are hybrid systems, where they'll have a megawatt boost converter that takes 900 volts and makes 2,700 volts out. It's the same architecture with just higher voltage and power. So this particular project I'm working on now, we're trying to use a lithium-ion battery pack that's 200 to 400 volts with a rated output power of 100 kilowatts. We want to boost up to a maximum of 1200 volts. We want a power density of 22 kilowatts per liter. That maybe is just a number, but I'll tell you the Prius 2010, its power density was 3.8 kilowatts per liter. And we want this Q to be greater than 60, where we work out the loss over the drive cycles that are used to measure mileage, gasoline mileage. This CAFE weighted Q is corporate average fuel efficiency. That's some specified city and highway drive cycles. We want to reduce the capacitor size as much as we can. We want to use high power ferrite planar magnetics, which are well known at the 100 watt level, but they're not at all known at the 100 kilowatt level. And I'll talk about what those are. We want to talk about how to control this. And it's a distributed architecture, and so it's appropriate to have distributed control. Here's the drive cycle. This is, again, the US06 aggressive drive cycle. We also have city driving and highway driving that you maybe hear in commercials of vehicles. The CAFE weighting is 55% city driving and 45% highway driving. They're just different drive cycles that look like this. Here's some models we have of our losses in our converters. And this is the predicted losses for a boost type composite converter over the US06 drive cycle. So we can model the conduction losses that are really the direct power losses, and we can model the AC switching loss and magnetics loss that are from the indirect power, and we get these plots, and you can see that the magnetics loss and the switching loss can be pretty significant. This is for a composite converter where we modeled the Prius. We have to model the weight and power of the Prius to what power does it take to do this speed profile. And then from that, we can model the losses in our converter system. And we try to then design the converter to optimize to get the lowest total loss over these drive cycles. Here's the shaded regions here are the predicted efficiencies of our composite converter system as a function of the output power. This is for the Prius, and the DC bus voltage. And this is over the USO6 drive cycle. So the blue lines are where we end up going over this 10-minute drive cycle as we accelerate and decelerate. So we go to high bus voltage when based on high speed, and we have high power when we're accelerating or decelerating. And then it's interesting to just see what happens. And you can see that we spend a lot of the time for this drive cycle up here. The USO6 drive cycle, again, is aggressive driving, and we go fast a lot. So we're at high speeds and have high bus voltage. The power, we don't ever get to 30 kilowatts. There's a peak right here that's about 25 kilowatts and another one there at 20. But, we don't use the full power very much. What we do a lot is use high voltage and moderate power. And so the efficiency curve is very important. And being able to produce high voltage, which is a high voltage boost function with high efficiency, is important, but we don't need to do it necessarily with very high power. So given that the vehicle does some trajectory around this plane like this, then it becomes an optimization problem of how to design the converter to minimize the total loss over a trajectory like this. And we run our computer programs for a long time to try to optimize all the variables. So again, for this, this is really the result of an earlier project that was purely silicon. So the Prius was this column. What we were able to do with a silicon composite boost converter was this column. And we were able to significantly increase the average efficiency of the converter. And as measured by this Q, we could go from basically 18 to 52, so a factor of 3 better. And the magnetics volume actually stayed the same, but the capacitor was decreased a factor of 4. And again, this was the efficiency curve that we were able to get through this optimization. Now let's add silicon carbide devices. So we can, the silicon IGBTs, you could get 1200 volt silicon IGBTs. That's what's in the Prius. For this silicon version, we use 600 volt silicon MOSFETs that had multi-level switching, which shared the voltage and let us use 600 volt devices. You can get 1200 volt silicon carbide MOSFETs. And if you simply replace the silicon IGBTs in the Prius with silicon carbide MOSFETs and leave everything else the same, you can get a higher efficiency because the silicon carbide switches faster and has less switching loss. So there is some improvement in this weighted Q, and that gives us a lower temperature rise if you just keep the heat sink the same. And the lower temperature rise gives us higher mean time to failure. So, better reliability. Um, if you use silicon MOSFETs in the composite approach, which is what we did before, we can get even higher efficiency with lower temperature rise. But the silicon MOSFETs, we need more of them, and then we need more gate drivers, and it actually lowers the reliability. It's better than what's in the Prius, but it's not as good as what you could do with silicon carbide MOSFETs. And then if we put silicon carbide MOSFETs in the composite architecture, we can get very high weighted Q, the lowest temperature rise, and the longest mean time to failure. Okay, so finally, here's what we're building now, which is this 1200 volt, 100 kilowatt device. We're building the final prototype now, and this is the power density we're getting. So 21 kilowatts per liter. The 2010 Prius was basically 4 kilowatts per liter. So it's a factor of 5 improvement in size and in power density. Instead of switching at 10 kilohertz, we're switching at 240 kilohertz. And so that lets us greatly reduce the size of the magnetics, and we also reduce the size of the capacitors. So magnetic core volume goes from 14 milliliters per kilowatt down to 3, and that's pretty big improvement in weight as well. Control. This is a complicated thing. There's 3 different converter modules, and the converters go in and out of pass-through mode. So the control is saturating. It can saturate in pass-through mode, it can saturate at the opposite extreme in shutdown, or its duty cycle can be controlled and it can switch. Here's a plot of what happens. So our DC bus voltage, what we've done is command a stair-step reference. So we have a fixed input voltage of, I think it's 250 volts or just under 300 volts. And we command the output voltage to step from 300 up to, in this example, about 750 volts. We could command it to step higher if we like. So the reference voltage is taking these steps, and in order to make the bus voltage follow this reference, here are the gate drive signals that go to the different modules. So this is the buck converter that's in the top leg. This is the boost converter in the bottom leg. And this is the DC transformer that's in the top leg. So for a low output voltage, we turn off the buck, so its drive is 0. We turn off the DC transformer, and we just use the boost. So we're making low voltages. At this point, we transition operating mode. So now we start switching the buck and start switching the DC transformer, and the boost it has 0 duty cycle. It's in pass-through mode. And so the boost is in pass-through, and we're adding some voltage from the buck and DCX. And then when we get here, everybody's on. And so we have the buck, or the boost is switching, the buck is actually in pass-through, and the DC transformer is running. And we're stacking those voltages to get a controllable output. So this is pretty complex control, and we have different modules to control. And we do this with a distributed or decentralized controller. So each converter module has its own local controller that is controlling the duty cycles of these modules, and it needs to stabilize them and produce output voltages that follow references. There's a central controller that's very simple. It's simply commanding the reference voltage for each of the individual modules. And by doing that, it can, in fact, push them into pass-through mode or shutdown mode if necessary. Or during transients, they can all run. to stabilize the transient. There's some also pretty interesting things that happen, like what if a buck converter is in pass-through mode, but there's a transient. So the buck converter has a resonance in it of its LC filter. And when there's a transient, like say the load changes or the boost module changes, it can cause ringing in the buck module. The buck module has to come out of pass-through mode briefly and switch under control to damp out the ringing, and then go back into pass-through mode. So it's a true distributed control system with local controllers that are controlling their individual modules according to high-level commands from a central controller. So we've developed this with a chill system. Excuse me, that's controller hardware in the loop. So basically the chill system simulates the converters being controlled, and then we program our digital controllers with the chill simulators to debug and get our controller algorithms to be proven before we plug them into the real power converter at 100 kilowatts. Just one other short thing, and then I'll be done. The power planar magnetics are interesting. Planar magnetics use printed circuit boards for the windings of an inductor or a transformer. And then we have ferrite cores that fit around slots in the printed circuit board. So this green board here is a high copper weight printed circuit board. Each layer of the printed circuit board is this wide trace. It's this wide, and it actually goes in a racetrack around this path. At the end of the turn, it goes through vias into the next layer underneath it to make the next turn. And there are multiple layers with multiple turns. So we're building these high power planar magnetics with ferrite. We're able to do this when we have switching frequencies higher than 100 kilohertz. And so we demonstrated planar magnetics at this 100 kilowatt level with switching frequencies of 240 kilohertz. The planar magnetics do require cooling. And so in the electric vehicle, we have a radiator and a liquid cooling system. So there's a cold plate in the converter with the radiator fluid passing through it. And on one side, we mount the power transistors for cooling. On the other side, we mount the planar magnetics. And we have to design the planar magnetics with thermal channels that can let the heat in the windings and the heat in the cores flow into the cold plate. So that's been a pretty interesting project in itself. But I guess we're demonstrating these then planar magnetics at the 100 kilowatt and several hundred kilohertz power levels. So conclusions then. I guess the claim here is that at these new applications that are enabled with high frequency wide bandgap devices, it makes sense to highly modularize the converter and use these more complex power converter architectures. And the reason is we get much higher performance. We can cut the loss by a significant fraction. It's not just an incremental reduction in loss, it's a significant reduction in loss, which leads to significant reduction in heat sink or cold plate, radiator size, and significant weight and size improvements. It's non-incremental, and the reduction in loss can also be used to reduce operating temperatures and improve reliability or lifetime. So we're using these partial power modules that go in and out of pass-through or switching or shutdown modes in ways that optimize the total of loss. And this is appropriate for higher voltage and higher power applications, which are being enabled by the wide bandgap devices. And this project is supposed to conclude next year. And there's this summit, ARPA-E, the Department of Energy Advanced Research Projects Agency, has a conference once a year where the projects are supposed to demonstrate their results. We're collaborating with Toyota on this, and so we're going to demonstrate this in an electric RAV4 vehicle at the summit. Unfortunately, last year Toyota discontinued the all-electric RAV4, so they don't sell an all-electric vehicle anymore. But I hope they will again soon. But we have one of these, and we're going to put it in there, put our prototype into the RAV4 in 2021. Okay, so that's I guess what I have, my presentation. So thanks for your attention.
Thank you, Doctor, for your presentation. Thank you very much. Okay, so I think we're gonna go to the questions. If somebody has a question, you can go ahead, use your microphone.
Hello, Ms. Ray. Can you hear me?
Yes, we can hear you. Go ahead.
Okay, thanks. Well, thank you, Doctor, for your presentation. It was really interesting. And I have a few questions about in the composite converter. It is important the local controllers, if you can, I don't know, if you can design more complex controllers that can measure and can, I don't know, can control the temperature that is in the converters, that will improve the efficiency of the composite converter at all? Or it's more important the architecture of the composite converters for the performance?
Yes, so good question. Really, I guess in this project, we're focused on the performance of the power conversion system. So minimizing the loss and minimizing the size. But the solution to do that is then a complex power conversion system that requires complex control. And I guess I'll say that we started trying to control the whole thing with a centralized controller. And every time we changed one little parameter in our design, the person in charge of designing the control system had to start all over again. And so we realized that decentralized control is needed so that, the control algorithm for the buck module is optimized for the buck module, and it's inside its local controller. And if you change the boost module, you may not have to change the control of the buck, for example. So the problem really is how to build a control architecture that works. And it's a highly nonlinear system. Yeah. The converters are nonlinear to start with, and then we are turning modules on and off and making it all the more nonlinear. And we have to have control laws for each of the local modules that works over this, wide range of operating points. And you do have to worry about interactions as well. And closed loop power converters are known for having negative incremental input resistances that are famous for causing stability problems. And we have those here also. So we do have to design control laws that correctly control the local controller, or the local module, but also the interactions between the blocks are stable. And
yeah, you can prove the stability of all also, you can prove the stability just from the local controller with the module, but not from the stability of all the complex converter at all.
That's right. So we have to prove stability of the whole system, we have to include the interactions.
Another question, Doctor, is have you worked with the sigma delta modulator instead of duty cycle?
So personally, no, I'm not the chip designer designing the pulse width modulators. So what we're doing in this project is we're just buying commercial, Texas Instruments microcontroller chips and using their pulse width modulators, which are counter based and delay line based.
Okay. Well, again, thank you for your presentation. It was really interesting.
Okay, thanks. Thank you.
Okay, there's a question from Jose Cruz. I'm going to read it. It's in the chat. It says, in the literature, for power electronics applications, what is the maximal transit frequency reported in silicon devices, and what kind of technology is employed in those devices?
Yes, so I would say in the 1990s, there were almost competitions of who could use the highest switching frequencies. And there were switching frequencies at 100 megahertz. So super high. They achieved good efficiency considering it was 100 megahertz, but the efficiencies were not as good as what you could get at 1 megahertz. It's a function also of voltage. The switching loss of the power transistors is proportional to the voltage that they block when they're turned off. And so we have, I guess in computer power supplies to power 1 volt type microprocessors, we have switching frequencies regularly at 1 megahertz. And they've been silicon in the, in fact, I'd say today they're still mostly silicon, but we're seeing a lot of GaN type converters used at those power levels. When you get to 10 kV, the other extreme that I listed for silicon carbide, the first boost converter built with silicon carbide at 10 kV was 8 kilohertz, which was amazing at the time. The silicon IGBTs at that voltage would run at 500 hertz. Now there are people maybe running at 10 or 20 kilohertz, but that's as high as they get. There are practical GaN converters for envelope tracking in RF transmitters that may run at 50 megahertz. Turning up the frequency is good, but if you need inductors or transformers, ferrite cores get smaller as you turn the frequency up until you get to about 1 megahertz. And after that, we don't have good ferrite core materials for power magnetics beyond 1 megahertz, and there isn't much point in doing it. I guess one other example, the little chargers for cell phones, little cube chargers that are like 1 inch. The latest ones have GaN, and they are switching at maybe 1 megahertz. And with the higher frequency and GaN, they're able to get more power. So the original iPhone cube charger was 5 watts, and now you can get GaN chargers in the same volume that are more like 50 watts. So another example why our high power density, in this case volume, is really significant.
Okay. All right. Thank you, Doctor. Is there another? Yes, here saying thank you, Professor. Is there another question? Well, in the meantime, I have one. So It's the first time I think that I've seen this composite architecture that you presented. This was this is already published somewhere in the literature?
Yes. So we've published it in the IEEE Transactions on Power Electronics, and also at this ECCE. So what's that? The IEEE Energy Conversion Conference and Expo. That's an annual power electronics conference. I think I have a couple of references listed. Let's see. Yeah, here are.
Oh, okay, yes.
Here are two of them.
So that was back in 2016. Yes, right?
Yeah, that was the silicon version.
Okay.
And since then, we've gone to silicon carbide and higher frequency and higher power.
Okay. There's another question here from Richie. He's saying, what is the disadvantage of using a boost converter? And if there is a risk of uncontrolled increasing the current or voltage?
So the disadvantage of just one boost converter instead of the composite, I guess.
Yeah, I think so.
Yeah. So that's what is in the 2010 Prius, is just a simple boost converter. And I guess I'm claiming, I think showing with experimental data, that with this composite architecture, you can significantly reduce the power loss by a factor of, well, you have different efficiency curves, but on the average, a factor of like 3 is what we've been able to demonstrate. And then we can also reduce the size of the capacitors and inductors along the way.
Okay, thank you. I have another question. So the I don't know if it's a prototype that you were mentioned at one of your last slides, the one that you're working with. These composite architectures, are you using, for example, for the modules, for the buck and the boost, are you using 2 transistors or 1 transistor and a diode?
Yes. So the converter is required to be bidirectional.
Okay.
So we want to be able to both, take power out of the batteries into the motor, and then to slow down, we want to use regenerative braking and have power come out of the motor and put back into the batteries. And for that reason, we need transistors that can conduct current, or realization of the switches that can conduct current in either direction. So we have transistors with anti-parallel diodes for every switch position. Yeah, I think, in fact, if we go back to the original, what's in the Prius, there's a transistor with an anti-parallel diode. And so we can have current go this way through the transistor, or go that way. I'm sorry, I drew that wrong. Current goes this way, will go through the diode. And if it goes this way, it will go through the transistor. And so in these modules, we do the same thing.
Okay. All right. Thank you. Okay, so there's a question from Luis. From the point of the academic productivity, I have seen that some of your highly cited papers are conference papers. Nowadays, it's requested to research to publish mainly on JCR papers. Which is your point of view about this?
Right. This is something that we faculty debate all the time. And the traditional viewpoint in academia is that the journal papers are highly regarded and the conference papers are not. In industry, it doesn't really matter, but in academia, then when faculty are evaluated, the journal papers are what is primarily counted. It is important anyway to go to conferences because conferences are where everybody gets together and talks, and where there are not just academics, but people in industry. So whether or not, you know, the conference paper counts for my annual evaluation and raise and whatever salary, the conference papers are still important, you know, to the career of a faculty in the power electronics area.
Okay, so I guess that's well, that's another question. How you were able to collaborate with Toyota?
That's you know, collaborating with companies is a good thing, but it's always a function of the personalities involved, and this project started actually as one with I guess Toyota in Japan liked, I guess, our research group in Boulder and sent one of their engineers to us to be trained in power electronics. And that started the relationship. And we initiated then a research project, which is kind of unusual, really. It was a research project between our university in Boulder and some of the power electronics people at several plants in Japan. And normally, you know, an international collaboration like that can be hard to initiate. But we did start it, and that really got us directed towards the power electronics of the Prius. Later, I guess our collaborators in Japan introduced us to researchers at the Toyota Research, you know, Institute of North America, which is in Ann Arbor, Michigan, and we started collaborating with them. And I think that's a more normal way for collaborations to happen. So Toyota does collaborate with entities in the United States, but usually it's through their United States subsidiaries. And that's what we're doing now. So the introduction had to be made, and these relationships only last so long. After a few years, the manager who was in charge gets promoted or moved away to somewhere else, and you have to start over again. So the lab, you know, develop a new relationship with a new person who's in charge, and that happens everywhere.
All right. Okay. There's another question from Luis. He's saying, do you have any recommendations for these students to pursue PhD studies? Are there some open positions at your lab or research stays?
Yeah, well, you know, we're always admitting new students. Certainly, in power electronics, you know, we want to see students that have a good electrical engineering undergraduate background, and you know, are able to build things. And so in power electronics, we like a combination of both theory and practice. And so for example, to publish a paper in power electronics, you can't just have math without experiment. the paper won't be accepted. And so the projects end up, and the best projects and the best results end up being ones that have some good theory and good math, and at the same time have some good circuits built that work. And these power converters, you know, are not so straightforward to build and make work. So some experience in building is good too. And so generally that's what we look at. The COVID situation, I think, probably everywhere, but certainly in the United States and certainly at our university, has disrupted things. So, you know, it's hard to get a visa to enter the United States, and some of our interning graduate students who are not domestic were not able to. I mean, the embassy closed in their country, and they weren't able to get a student visa to attend. And we're all just making do right now. But I think that will be over soon, and hopefully we'll be back to normal. And I hope next year, when students enter in the fall, it'll be back to normal. So
Okay.
So
yeah,
yes,
let's hope.
if you like power electronics, you certainly apply. And, yeah.
Okay, nice, thank you. Jorge Luis is asking, how limited is the technological application with respect to scientific research, specifically in the construction of semiconductors? Is a limitation for power electronics?
I guess to run a research program, I mean, my job to a large, or part of my job is to attract research funding to support students and graduate students and be able to do the research. And so then we have to have an application that somebody wants. And so maintaining the research program really does require me to pay attention to what is the application. And, you know, we get research funding from private companies and from the US government. The US government has their own ideas. Their program managers have their ideas of what applications they want. Generally, they aren't interested in theory. In power electronics, what they want is for us to build a box that does something new that they want. And so we have to justify our project according to what they say they want. And then hopefully along the way, we get to do some good theory and advance the theory of the field as part of the project. But nobody is really giving contracts for just pure theory, unfortunately. So I look back at my graduate school days fondly as times when I could sit in my office and think and do theory for most of the time, but it's not really how the world works. It's certainly,
Okay.
I don't know if that answered the question or not.
Okay, thank you, Doctor. So I think we're gonna finish here. Finally, I understand that your thesis advisor was Dr. Shook. Is that correct?
Yes, Dr. Chuk and Dr. Middlebrook, but yes, the primary advisor was Dr. Chuk.
And they were like the first researchers in this field, right? In power electronics?
Well,
one of the first?
They were early researchers in the field, yes. I mean, people were doing research on power electronics in the 1920s. But I think what they were most known for was developing average modeling of switching converters. And that really, Middlebrook got started doing that consulting for TRW, which was the company in Los Angeles that built satellites. And in the 1960s, they were building switching converters on satellites, and their feedback loops oscillated, and no one knew how to predict the dynamics or the transfer functions. And that got Middlebrook working on it back at Caltech, and I mean, you know, led to the basic results that he and his student at the time was Chuk. He had some other students along the way too, but then they hired Chuk to be on the faculty when I was an undergraduate, actually, and then they built up a research group that got pretty large, especially in the 1980s.
Okay, so that must have been a nice experience, huh?
Oh yeah, it was great.
All right. Okay. Well, thank you, Doctor. I think there aren't more questions, so I'm gonna read recognition. I'm gonna share my screen. Let me see if I can do that. Here it is. Okay. Oops. Okay, so I'm gonna read this recognition. It says Certificate of Recognition to Robert Erickson for his video conference, Complexity and Modularity in High-Power SiC Converter Architectures, given in the Center for Digital Systems Research and Development on December the 18th, 2020, and the signature of Dr. Julio Cesar Rolón Garrido, Director. So thank you very much, Dr. Erickson, for your presentation. We will be sending this recognition by mail, in your email.
Thank you very much. That's very nice. Yeah.
Okay, so maybe we can keep in touch later. Thank you, Doctor.
Yeah, okay,
Okay,
bye.
Bye.
Thank you, Professor, for your participation in this activity. I think for the students it's good to hear some news or some information from abroad. And thank you for helping us with this activity.
Yeah, my pleasure. Thank you very much. And goodbye to everyone.
Bye-bye.
Bye.
Right.